In this video, we're going to talk about the currents that flow in a p-n junction. We need to examine current flows in p-n junctions because we're confronted with a paradox. Common sense says that diodes don't make current without some externally applied energy, so we can't hook up a diode to a flashlight and expect it to light up. However, we've got this E field inside of our diode which will cause carriers to move. So why doesn't that make current shoot out the edges of the silicon? I'd like you to take a minute to guess. So pause the video and write an explanation for yourself about how to resolve this. The resolution is that the E field isn't the only thing that makes charge carriers move around in p-n junctions. There are actually two ways that charge carriers move around in junctions, and we call those two carrier flows by different names: diffusion and drift. The two carrier flows cancel out at equilibrium, which results in no net current flowing through the junction. The first carrier flow is the one that got us into this paradox trouble in the first place. Minority carriers on either side of the junction see an electric field pointing towards the opposite side. So if a minority carrier stumbles into the junction, then it's swept to the other side by an electric field. This phenomenon is called drift. It results in a current that points in the negative x direction because holes move along the E field in the negative x direction, and electrons move in the opposite direction of the E field because they're negatively charged in the positive x direction. Because electrons have negative charge, moving them in the positive direction creates a current in the negative direction. Also, note that the negative charge on electrons means they move in the opposite direction that the E field points in. The second type of current is called diffusion. It comes from the random motion of majority charge carriers, which results in carriers preferentially moving from areas of high concentration to low concentration. However, only energetic carriers can diffuse successfully across the depletion region because the E field is exerting a force in the opposite direction of diffusion. You can conceive of that effect instead of as a force pushing on diffusing atoms as an energy barrier that diffusing atoms need to cross. So we can imagine that this built-in voltage creates an energy barrier of a height that's equal to Q times VBI, where Q is the charge on an electron, the sort of fundamental charge. So only carriers with energy that happen to randomly be higher than that energy barrier will hop over it to the other side. Diffusion current points in the positive x direction because it causes holes to move in positive x, and electrons to move in negative x, and electrons moving in negative x creates a positive x current. Also, just one final notational note, I drew these diffusion arrows as kind of curvy because I like to imagine a big pile of electrons spilling over the edge of a barrier. That doesn't have any technical meaning, it's just an aesthetic choice to differentiate it from the drift. Applying a voltage to a diode unbalances the diffusion and drift currents by changing the total electric field in the p-n junction. So that allows current to flow through the diode. This process is complicated, and we're painting a really simplified picture on this slide for expediency's sake. So if we apply positive voltage to the P side of a p-n junction, which is a condition referred to as forward bias, then an external E field pointing in the opposite direction of the built-in E field, which goes from P plus to B minus, will be present in the diode. Those two fields will cancel out partially because E fields add. The dynamics are complicated though because the external field also pushes some charges around. However, the upshot is that the external field results in a reduction of the height of the energy barrier that electrons need to cross, which I've pictured over here. So this reduction in barrier height means more charge carriers will diffuse across the depletion region. To figure out how many more, I'm going to make a quick analogy with something that you've seen before. There are similarities between carriers crossing an energy barrier and chemical reactions, in the sense that both involve thermally distributed particles overcoming some energy barrier to do something. And so you may have seen a similar equation to this exponential down here in chemical reactions, where you compare an energy barrier, and in this case we're talking about a change in the height of an energy barrier that's equal to Q times Vd, against thermal energy, kT. So the ratio of thermal energy to a barrier height helps you predict the probability of some event happening. And in this case, it's the probability of transit across a p-n junction, how likely it is for a carrier to make a hop from one side to another. Now, I've left VBI out of this equation because we're considering a change in the probability of transit from equilibrium. So QVD represents a change in energy height from like the barrier that's always there that's equal to QVBI. We'll bake VBI into a different constant later called IS that captures how much current is moving back and forth at equilibrium. Also, just as a note, K is the Boltzmann constant and T is the temperature. Now there's one parameter that I haven't mentioned in this equation yet, which is N. That's called the non-ideality factor, and it's just to capture impurities and other things inside of the p-n junction that can cause current transfer to be less effective. So I go through this extended analogy between probability of transit across the p-n junction and a chemical reaction in order to point out that we would expect an exponential change in the number of free carriers that transit across the p-n junction as we change applied voltage, because we're doing this sort of a thermally distributed energy comparison. So the fact we're crossing an energy barrier with thermally excited particles means that we are exponentially sensitive to the height of the barrier. Now, if we apply a reverse bias to the diode, you can see that our voltage source has switched directions down here. We're going to wind up with an increased E field because the external E now points in the same direction as the built-in E field. And that raises the height of our barrier, and by the same logic as the previous slide, that means our diffusion is exponentially decreased. So applying a reverse bias essentially shuts off diffusion. So that means drift current is the dominant form of current in a reverse bias. However, drift current isn't increased by having a bigger E field. Minority carriers were already being swept all the way across the p-n junction if they stumbled into it at our normal E field. And the amount of drift current was limited by the number of minority carriers, not by the size of the E field. So changing the amount of reverse bias essentially doesn't affect our amount of current because drift is not limited by the E field in the p-n junction. However, that kind of breaks down if the E field gets high enough. If you apply a really big reverse bias, then carriers in the depletion region start moving very fast. And if they move fast enough, they can also knock other electrons loose when they collide with atoms. And those electrons are also accelerated by a high E field. So that results in a chain reaction of free carriers that's called avalanche breakdown, which is a great name. Having a high peak E field causes this chain reaction, so reverse bias will eventually cause p-n junctions to avalanche. So in summary, minority charge carriers are pushed across the p-n junction by the built-in field, and that's called drift. Energetic majority charge carriers can randomly jump across the p-n junction, and that's called diffusion. Drift and diffusion are balanced in equilibrium, but diffusion exponentially increases under forward bias or decreases under reverse bias because an energy barrier is being lowered or raised, and we picture that energy barrier as being related to the built-in voltage. On the other hand, drift is limited by the number of minority carriers, so it's unaffected by the strength of the electric field in the depletion region.